good afternoon for those who are in Europe, and good night for those who are in Asia. It's a great pleasure to have the chance to present in this seminar. I will discuss today what we have been doing in the last few years related to the energy harvesting area. This work I will show here was developed by myself in collaboration with several students and a postdoc and some colleagues. Okay, my collaborators in this research is Vinicius Lopes, who is in this meeting, João Peterson, a former undergraduate student, Leonardo Roca, which is a current undergrad student, Marcelo Pereira, a former postdoc, José Geraldo Teles, a colleague, assistant professor, and Albert Macau, a colleague, full professor from another university. Okay, I will start showing a picture, and I know that those of you who lives in Europe perhaps know where is this located, and some may not know, so I will tell you. This is St. Peter Square in Vatican City. Okay, you have a picture of the same place, but in two different time moments. The top picture was in April 4, 2005, and the bottom one was in March 13, 2013. This is the event that follows the death of John Paul II, and this is the events related with the beginning of the pontificate of Francis. Okay, you have 8 years. You have a time difference of 8 years, and you can see that in 1 decade, almost, there is a big difference in the cultural habits of the people here. You see here, you can see some electronic devices, digital cameras, with few people here, and here is completely different. Almost all the people have an electronic device, a tablet, a cell phone with camera. Okay. Now I'd like to move for another picture that show a certain object that I'd like to ask you in the audience, if is there anyone here that knows what is this subject? If there is, you can open your mic and say, what is this object?
It's a medical implant?
It's a pacemaker.
Yeah, it's a pacemaker. Perfect. Okay. I hope no one in the audience needed to use this, but a lot of people in the world needed to use, and it's extremely vital. Well, I'd like to ask a question now. What both situations have in common? The agglomeration of people in Vatican City and the pacemaker. Well, the people there are using electronic devices, and pacemaker is not. It's a kind of electronic device, and both objects need energy. So you need to power this. But these are, in some sense, portable devices. These you carry with you whenever you go, wherever you go. And these, for those who use, transport these all the time, but inside your body. The lifetime of this kind of medical implant is determined by the lifetime of the battery. And the usage of this device is also limited. The bottleneck here is the time of life of the battery. You can recharge these every day, but one concern that everybody has nowadays is, oh, I'm going to travel, I'm going to airport, I will spend 20 hours traveling. How can I charge my phone during this time? So this kind of new technology imposed some challenges in how can we power this without using the electrical system, okay? How can we enlarge the life of these devices? Because to implant this in a person, you need to open the body. It's a very invasive surgery. And I use this all the time, every day. So I needed to charge this frequently. How can I reduce the time of charging, so that how can I increase the autonomy of these devices? Okay, energy harvesting is a technology that Emergent trying to give a solution for this kind of problem. In this talk today, usually I started from very basics when I give this talk, okay, but here, differently from what I'm used to, I have an audience which has some of the greatest experts in the world in this subject. So I will not go so basic. I will talk a little bit about the basics because we have some students that may not be used to may not be so familiar with this kind of technology. So, but I will concentrate more in some technical details during the talk, okay? So, a brief introduction in the beginning, then I will move to talk about a certain dynamical system, a classical vibration energy harvester that I have been studying with my collaborators. And in the third part of the talk, I will talk about how to control this kind of device, especially in the case when it presents chaotic behavior, and I will conclude the talk with final remarks. So the introduction, the subject of interest is energy harvesting. The basic idea, just to those who are not familiar, is in energy harvesting, you are trying to capture, I like to say you want to steal energy from an environmental source which has a lot of energy available for free. Okay, like sun, wind, vibration. So you use a device called the harvester for this. The harvester, essentially what it does is it capture energy here and put and store it in a certain kind of secondary device, a battery, a capacitor, for a further use in the application that you need this energy, okay? So this is not a new idea. You have many classical devices that operates according to this principle, okay? Water wheel, electronic watch, satellites, aerogenerators, heat systems in-house, but this is not the kind of energy harvesting system that we are interested in here. We are more interested in the emergent technology based on this principle, and this encompasses essentially mainly electronic devices, small electronic devices, microsensors, okay, all kinds of sensors that are demanded for Internet of Things, and my favorite subject in this area, medical implants. Several types of medical implants that try to use the energy available in the human body to power the medical implants, like pacemakers or sensors to monitor another activity of the body, etc. Okay. What made energy harvesting different from renewable energy, for instance, is the power scale involved. Okay, when in the renewable energy technologies, the domain, the scale of energy involved include kilowatts, megawatts, gigawatts. It's large power. This is a large power technology. In energy harvesting, the most interesting things occur in the small scale. Your domain of interesting goes from the nanowatt up to a single watt. Okay, so this is the scale of energy we wanted to concentrate. And as most of you know, you have several types of technologies that can be used to harvest energy: vibration-based, contact-based, temperature-based, heat-based, light-based, fluid flow-based, radio frequency-based. The focus today is vibration-based energy harvesters. And the classical prototype of vibration-based energy harvesting is sketched here. It consists of essentially a beam, okay, with a tip mass here, and this beam is coupled to a certain vibratory system, and the goal is to store energy from this vibratory system. this beam, you have a certain piezoelectric transductor, okay, which is represented by these green layers here, and this is coupled to a certain electronic circuit. And this piezoelectric transductor, what it does is it transforms, it converts mechanical energy into electrical potential that can be used to power your application, okay? The bottleneck of this technology is that the efficiency of this system, it's extremely low out of the resonance of the mechanical system, okay? It only can recover a significant amount of energy very close of the resonance configuration. So in the end years of the first decade of this century, people arrived with a great idea. Let's try to introduce nonlinearities in our harvester to increase its efficiency in a broadband frequency of operation, okay? So that we can recover significant quantities of energy far from the resonance. And in the context of vibration energy harvesters, one of the pioneers' works is this one developed by the Italian group from NIPS Lab, which includes Francesco Cottoni, Elios Voca, and Professor Luca Gamaitoni. And they proposed this device here that you can see. It's essentially an inverted pendulum driven by a stochastic excitation with environmental noise. And this is essentially a bistable system. And they showed that you can recover significant amount of energy in a broad band of frequency. In the same year, Alper, Turk, Hoffman, and Daniel Wieman introduced this idea in the engineering community with this system here that perhaps is the most studied vibration and nonlinear vibration harvester in engineering community. Well, this system is the main system of interest of this talk. Okay, all the results that I will present are related to the system, so I will spend a minute describing its configuration. It's a rigid base. Attached to this rigid base, you have a beam, a deformable beam made of a ferromagnetic material. In the base of the rigid base, in the bottom of the rigid base, you have a pair of magnets. And this pair of magnets will induce large vibrations in this beam. The rigid base vibrates according to a certain harmonic signal, okay? And in the top part of this beam, you attach a piezoelectric transducer so that it can capture the kinetic energy here. It can transform the deformation and the energy related to the deformation of this beam due to the inertial effects induced by the base into electric potential, okay? We have been studying this system for almost for 40 years now, and we made a lot of studies. I will not talk about everything we did in this system today. I will concentrate myself in some parts, okay? I will show some time series, some Poincaré sections, bifurcation diagrams, and Basins of attractions. This is our first goal with the system, try to understand in deep its physical characteristics, physical phenomena that you can observe in this bistable harvester. We are also interested in, more recently, in the last year, we concentrate our attention in study the stochastic aspects of this nonlinear dynamical system. And we were studying some strategies to optimize the system by exploring some control of chaos techniques, okay? I will talk about today a little bit about what we studied on the basic dynamics, a little bit about of the stochastic dynamics, and about control of chaos. Well, what I will talk about the basic physics doesn't bring a lot of novelty for this audience that is made of experts, but we spend a lot of time in this to understand better this system. This was a learning process for us in the group, okay? And our more the content which brings more novelty is related in these two parts. I will talk more for the end of the talk, okay? So let's start with the linear dynamics. If I remove the pair of magnets, this becomes essentially a linear oscillator, and you can see a graphical illustration of this dynamic system here, of these dynamics here. Well, it oscillates. Okay, you have a brief transient that it disappears, and it responds harmonically. This time, this is the displacement of the beam tip. And you see that the amplitude of movement of the beam tip is not very high here. So in principle, you don't have a lot of energy available to collect. This amplitude will be increased a lot if I excite the system with the resonance frequency, but it's not the case here. So if you see here some bifurcation diagrams for this dynamic, for this linear dynamics, where you can see the voltage as function of the excitation frequency for several different values of the external force amplitude. These diagrams were constructed by Vinicius, who is here. You can see that the only interesting thing that happens with this dynamics is the resonance, okay? But when we move to the nonlinear system by introducing cubic nonlinearity, which transforms this mechanical oscillator in a Duff system, okay, coupled to an electrical system, the dynamics become much more interesting, as you can see here, okay? You see the same external excitation configurations as in the previous case, but the response now is aperiodic, okay? And if you pay attention in the amplitude of the movement was enlarged. So by introducing nonlinearity, you may increase the amount of energy available of the resonance. So when we started to study system, we decided, oh, we needed to understand in deep this dynamical system. For some experts, it's trivial, but for us, we are starting, it's not so trivial. So let's study in deep. And I picked some undergrad students at that time, and let's study the bifurcations and the Basins of attractions and other nonlinear features of this system. And you can see here the same collection of bifurcation diagrams I showed before for the linear system, but now for the nonlinear system. Okay, we have the voltage, the voltage as function of the excitation amplitude for several different frequencies. And in a few minutes, I will show you the opposite, varying the frequency for several different amplitudes. And look what we can see here as I move the frequency. You can see that you have many chaotic regions, and you have a coexistence of solutions, something that in the linear system you don't have. Okay, and when we go in deep to see the time series, to better appreciate the characteristics of the coexistent solutions, you can see that you have a low amplitude solution coexisting with a high amplitude. So you have much more energy in this one, and so it's our goal to try to capture this one. You may also see some aperiodic behavior like this, coexisting with a periodic one. And now let's investigate the effect of the frequency. Here I show voltage as a function of the excitation frequency for several different excitation amplitudes. And you see that the coexistence of solutions persists, and a very rich dynamics with several intermittent chaotic regions can be seen for some amplitudes. Okay, and when we go to the time series, you see a very rich, very complex dynamics, and you see some frequencies for which you have two periodic solutions coexisting with high amplitude. Sorry, this is a low amplitude. The scale looks high, we see that it's not so big. So here are the bosons of attractions to see how the initial conditions interfere in the response of the system. Okay, you saw many coexisting solutions there. So here we can see two, and I will vary the excitation frequency. You can see that as the excitation frequency is varied, a lot of solutions are changed, constructed, and destructed, and you can see some kind of erosion emerging in the boson of attraction of the system. Okay. So this is a little bit classical, but I believe there's no study in literature who investigated these bifurcation diagrams and bosons in deep as we did. Unfortunately, we didn't publish this yet, but we are working on this. We hope to submit this paper soon. But now I will concentrate in what we did, which brings more novelty, the stochastic aspects. Okay, the classical system is driven by harmonic excitation. But our goal now is to see the combined effect of an harmonic with a noise excitation, because in the real environment, is this what you're going to see? You're going to see maybe an harmonic excitation, but disturbed with some noise content. And to this, we added some noise in the mechanical equation, okay, which is related to the excitation induced by the movement of the rigid base. And we considered for this stationary Gaussian noise with this correlation function that you can see here. This is a colored noise function, not a white noise, which is studied in literature. We decided to model this noise as a colored noise, a stationary colored noise with this correlation function is zero mean. Okay. You can note that this correlation function is parameterized by two numbers: the standard deviation, which gives the noise amplitude, and the correlation time. And some experimental tests show that these parameters are not independent. So we decided to make the study. We are conducting studies trying to see the effect of this ratio in the dynamics. Okay, this is an ongoing research. So, stop it again.
It stopped again. Yeah.
I don't know what's happening. Can you see again?
Yeah, it's okay. It's okay.
I'm so sorry. I don't know if it's my fault, but I'm so sorry.
Again.
Let me try to. I close the browser. Maybe is this okay?
Okay.
What I'm showing here is the external excitation as a function of the noise intensity. Okay, and I remember you that I'm varying the correlation time according to this ratio. So here is 1% of noise. You barely see any difference in the external excitation. Here is a medium level of noise. You can see some difference. And something very interesting happened when we enlarge the amount of noise. You change the correlation time here, and you can see that changing the noise intensity here can induce a kind of stochastic resonance in the input of the system. And what we are concentrating our attention now is to understand the effect of this stochastic resonance in the input, in the output, in the power recovered by this system. Okay, I will show an animation. Unfortunately, I don't have much more results to show you this. We started to work on this subject recently. But you can see that the dynamics, but it carries some difference compared to the aperiodic response due to the chaotic behavior alone. And what we are concentrating our attention is in try to understand this difference and see how it can be explored in order to harvest more power. Okay, one of the ideas that we are trying to explore is what I will talk next. That is control of chaos in this kind of system, okay? So controlling chaos. The typical here I show you two typical time series for the oscillator. Okay, one where you have a certain transient, a chaotic transient in the beginning that disappears, and after that you have an harmonic. You have here a time series where the chaotic response disappears of a short transient, and you have an harmonic content after that. And you have here another typical behavior is that during the operation window that you are interested in, the chaotic regime doesn't disappear, and you have a full chaotic response during all the time of the operation. Okay, you can see the two attractors that are associated to the behaviors I just shown. Here you have a regular attractor, okay, you have a regular limit cycle here, and here you have a strange attractor, okay. The first behavior there is the dynamics evolve sometime around this chaotic attractor and then accumulate in this one, and in the second time series, during the whole operation, you stay around this chaotic attractor. And how do I know that this is really chaotic? Okay, look the Poincaré sections. Here, clearly, you have a period 1 orbit, okay? And here you have a chaotic attractor because the Poincaré section is completely irregular. You don't have a regular shape, and you have an infinitude of points. So in the first case, this is a typical steady-state response, and in the second case, this is the typical steady-state response. I'd like to remember you that our interest is using the power generated by the harvester to power electronic device. And for electronic devices, this is the behavior you'd like to see. You don't want to see this. Why? Because in order to use usefully the energy embedded in the signal here, you need to rectify. You need to treat this signal, and during this process, you can spend a lot of energy so that this can make the operation not feasible. Okay, you can spend more energy that the energy recovered. In this case, the concept of energy harvest lost its sense. Okay, so this is not desirable in many situations. So how can we transform this in this sense? We know from the theory of dynamical systems that in a strange attractor like this, you have an infinitude of unstable periodic orbits embedded in this chaotic attractor. So the idea here is let's try to stabilize the harvester dynamics in one of these UPO and see if this is this and if we can recover a lot of energy doing this. If we can keep recovering a lot of energy in doing this. Chaos is not a new subject. It's 30 years old by now, but it's powerful. And in this context here, it can be a very useful tool to exploring deep the potential of harvesting technology. The classical methods of control of chaos are the OGI control technique and the Piragas control technique. This is a discrete technique of control, and this is a continuous one, okay? In the first one, the idea is to give small kicks in the system during its evolution so that you can keep the system in the unstable periodic orbit that is your target. And in the second one, you disturb the system with a very low amplitude signal so that it can keep the system evolving in the unstable periodic orbit that you're targeting in. And in case it started to leave this orbit, you increase the magnitude of the signal so that it can be moved back to that orbit. We are going to explore here mainly this first technique. We are still trying to make advances in the second one. So the idea is to apply a feedback control law. You have the harvester here, okay? You're going to pick a feedback from the output, okay? And you're going to apply some certain, you're going to compare this with a certain target and use a chaos controller to actuate in the system so that you can drive the system to the desired target orbit. Here you can see the uncontrolled system, okay, in a chaotic response for that harvester. And here in the left, you see the OGY, Odd-Grebold-York controller, and the Piragas. You can see that when you turn it on after a short transient, we can stabilize the system in this pink orbit. You can see here, okay? These are the results for OGI. The uncontrolled system, you can see here the aperiodic voltage, okay? But after we turn it on the controller at this point, you can see that very quickly it stabilizes in an unstable periodic orbit, and it's a high amplitude orbit, which is good because it has a lot of energy available for recovery, okay? But let's try to explore in deep what this technology is capable to offer, okay? So here you have the controller dynamics, and in the right I'm showing the power, the output power as function of time, okay? The blue curve is the power signal as a function of time, and this black line is an average, okay? It's a time average. So on average you have 0.01 dimensionalized units of power here, okay? Let's turn it on the controller, okay? And I'm stabilizing the system here in a period 1 orbit of high amplitude. And I ask you to pay attention in this line here. When I turn it on the controller, it almost doubled the average power, okay? So almost 100% of gain in efficiency using this. But when I try to stabilize in this period 2, I have the opposite effect. The amount of power available decreases a lot because this is a very low amplitude orbit. And you may also have this effect here. Here I'm using a period 5 orbit, and you barely see any change in the amount of power recovered, okay? Let's compare in details this time series, okay? This is the uncontrolled system, and this is the controlled stabilizing the period 1. You can see the difference of magnitude here. This is another amplitude. Here you can see that the average level of power is reduced, and here you can see a case where you barely see a difference, okay? I call this the magnification, the reduction, and when the effect is kept, when the power recovered kept constant, the good, the bad, and the ugly. So you may have good results, bad results, and ugly results with this kind of controller, okay? This table synthesizes the experiments we conducted, okay? You can see 7-8% of enhancement in the power. You can double it, but you can reduce it to the half. You can make almost unchanged. So how frequently is this? How, for a different set of initial conditions, how frequently you have an amazing magnification, a significant magnification, a significant reduction? We are working in this. We were working because Marcelo was conducting this, a postdoc fellow, but he found a good job, and unfortunately he left the group. Good for him, bad for us, but we're going to restart this. I hope to restart this research soon. So some final considerations. As we know, nonlinearity may be a powerful ingredient for harvesting efficiency, may induce large amplitude responses, and this is good from the energy recovery point of view, okay? Nonlinearity may also be an enemy because when you have a periodic, very chaotic behavior. This may not be good in terms of use of this energy. And you see that control of chaos may be a useful tool with good, bad, and ugly behavior, which need to be explored in deep. But the very large magnification, enhancement of the power recovered that we can see give us good thoughts that we can explore in deep this technology, this kind of technique to enlarge the efficiency of harvesting technology. And many challenges open. This is a numerical study, how to implement this in a lab, in practical devices. Okay, all of these are open questions yet. And if someone wanted to give some ideas, they're very welcome. Okay, what we currently doing? We are concentrating our efforts, especially in the study of the stochastic dynamics, and we wanted to see also explore more the Piraga's control law here, and made a statistical study on how frequently the OGI provide great enhancements of the power recovered. Okay, I'd like to thank a lot Professor Jagoshlik and Dr. Piotr Wolfsbach for the invitation for this talk. It was a great pleasure for me to present this to so distinguished audience. I also like to acknowledge some colleagues for a very useful discussion about the several aspects of the research I presented today for you, Professor Gamaitoni from University of Perugia, especially Professor Aline, Paula,